Welcome everybody. I'm really excited to be here. So electricity is something that is one of the most integral parts of the economy, the world. And so tonight I'm going to share some of I'd like to call them like war stories, the good, the bad, the ugly, and then we'll dive into, what is an electrical grid and how to develop one that, will work for the future. I mean, you think about where we'll be in 50 years, where we were at 50 years ago. We were just landing on the moon. Who knows, in 50 years, are we going to be building a colony on Mars or on the moon or different parts of the world? So these are one of the first things that you have to be thinking in your mind when you're exploring is, I need an energy source. And of course, energy is a little bit different than electricity, but electricity is what is going to make a lot of the tools function or wherever you go and explore. So on the first page here, we have two nuclear reactors. And so that's usually the source of where the electricity is created. And then you have in the middle, your HV, your high voltage transmission distribution lines. So that electricity it's like the freeway of electricity. And then somehow it's got to make it to your home or the end user. It might be a project, it might be a car manufacturing facility, but somehow it has to get from point A to point C. And as we'll learn tonight, it has to be very, very reliable. So this is just one of the old school pictures I figured I'd dig up. So I believe we have a Caleb DeBell online somewhere, and his father is right here. Me, apparently I was looking somewhere else, but with the red backpack. But that was one of the 50-miler hikes we did for our summer camp. That would have been back in 1990, probably 1991. So seems like yesterday, but to y'all, that's light years ago. All right, so one reason you're probably all here because somebody inspired you. And when you think back to who inspired you or why, maybe you had a curiosity in a video that you saw online, maybe a YouTube video, maybe as your father, mother, a friend, a scout leader, could have been a teacher, but it was someone or something had a spark inside of you. So for me, the person that inspired me was my grandfather. So not a lot of people know this, but he was the designer, he was the project manager of the booster rockets of the space shuttle. So these were his babies for 30 years. So that's kind of more of a black and white picture of it. But, Albert Macbeth, in appreciation of your dedication, efforts in assuring the successful accomplishment of this major space shuttle milestone, the first solid rocket motor firing. So back in 1977, and then you had the American flag on the first space shuttle mission come back, and we have that in my father, they have that in their house. But anyways, he was the person that inspired me. And so it took quite a few years for that to kind of click, but probably because I did so much cycling when I was younger, did a lot of racing, but he would play with me. We'd have dump trucks, and he was my hero. And of course, when the Space Shuttle Challenger blew up, he spent quite a bit of time in Huntsville, Alabama, having to testify and figure out, what went wrong. And so I learned a lot about quality and the source of the defect. And there's a lot of things that still today have never been presented publicly based off of that accident investigation. So if anybody ever want to learn more about the Space Shuttle Challenger someday, you're welcome to reach out to me and I'll share as much as I can. A lot of his retirement letters have a lot of interesting things in them. All right, so what are different sources of electricity? Probably the ones that, and you don't have to answer this question, but all of us are on computers, so we're all using Zoom. We probably have a light somewhere, and so a lot of people don't really. I mean, it's just so common practice. You don't realize where it came from. And electrons, they don't care actually where they came from. So it's not like I'm getting, like Mr. Macbeth's getting electrons from a windmill, Brian's getting electrons from a nuclear power source. But electrons, once they're created at a source, they go onto the grid, and it's a common electron. So that can come from like a nuclear power plant, a windmill, a biomass. And biomass is, some places grow corn and they'll use that as their fuel. It's usually some kind of product that you can burn. Solar, geothermal, which is, there's a picture there that I have that's this one right here. And this is real popular up in countries like Iceland. And so they'll drill down to where they hit a hot thermal source, and it'll create steam, which will be fed up into a turbine, and it'll move a turbine just like it would in a power plant. Then you have hydro, which, we've all seen dams, hopefully, in our different states that we have. So, you build a big obstruction, which has a hole in it that feeds it downhill, that then it goes and spins a turbine. And coal-fired power plants are very popular in West Virginia, different areas. They're getting phased out more and more in the United States. But even though what they say on the news, there's countries like China that right now they have more coal-fired power plants under construction than what we, the United States, have ever built. And so a lot of them will be idle, but they're in preparation for, if they ever need to use them, they can just start them up and they'll have that energy source. One of the most important things in an economy to get it running and productive is an available power source. And if you don't have that, especially on the commercial side, people that build cars or manufacturing, that shuts down very quickly. And then there's natural gas. So in the United States, natural gas is, in the past 15 years, has really taken off. And then here's a question for the group, food for thought. Why do we not include batteries on the list? Because you hear about that quite a bit, like batteries for electricity. And then if they're not on this list, what list would they belong on? Anybody have any ideas why it's not on the list for a source of electricity? And if not, what's the name of the list that it would be on?
Laboni, do you want to unmute yourself and?
Yeah, sure. My guess would be like, because it's rechargeables, like it has to be charged.
Yeah, you're right. So it would be more under a storage. So it's something that doesn't necessarily produce electricity, but it's something that stores electricity. And so it would be under a list called storage. And so, for example, in the United States, some of the storage devices we have, or we do have hydro storage. And so we built a lot of this in the 1970s. And what it is as water goes down a river during the nighttime, it gets pumped up back into the dam, and then it gets released and creates a source of electricity. So if you have surplus, like wind that may not get utilized, they can store it while the times that the people are not using that peak demand, they'll pump it back up into the dam and then store it to a time that you'll be needed. And batteries is that same concept. Let's see. So barriers to develop in a greenfield power project. Probably the biggest one is not in my backyard. And what does that mean? So people have ideas, electrical engineers have ideas, project guys and ladies have ideas that they want to develop something. But when you go to develop something, you have a lot of stakeholders that have interest in that location of where you're planning on building. And so a person might think, well, I have a wind farm. It's the best thing for the economy for this area. And what happens is you go before the city council and say, I'm going to put a wind farm on this potato field or wheat field or out in the ocean. And then all of a sudden the oyster farmers are like, no, that's where I go fishing. The person that says, well, that's my farming land. If you pay me for it, you can use it, but then the neighbors may not want it. Or if you build a nuclear power plant, that goes through many years of approvals. And you have cities, you have even states. You might have states that aren't even associated with your state. You might have, let's say if you build a nuclear power plant in Tennessee, but the fuel has to come from Idaho where they make the fuel rods, but that fuel has to travel by train over, Kansas and Colorado. And so they may petition to not have that fuel transported. And so you have to work through all those approval processes before you can actually, break ground. So permitting on some of this may take multiple years. Scalability. I think Elon Musk said here recently that one of his biggest challenge is the scalability of his product. And you'll find this out throughout your careers. So remember this from this presentation, is it's really easy to build something that's small. So something that fits on your desk, or something that you can replicate for your house, something you can replicate once for your boss. But it's a different beast when you have to do it 10,000 times over and over and over. In the United States, we have, I'll take a real life example. So there's a centrifuge. So when you enrich uranium, when you take the U-238 molecule, and then enrich it to get it towards a 3 to 6% enriched piece of something that it goes into the what's called snowflakes, but where you can put it into a reactor. So centrifuge technology is probably one of the cheapest, best technologies to do that. And in the United States, we've still not figured out how to do it reliably on a grand scale. We can figure out how to do 1 or 2 centrifuges, but there's a company out of the Netherlands, Great Britain, Germany, France. It's a consortium called ETF, Enrichment Technology. And my company that I was with ended up having to pay $500 million to join their company so they could build this centrifuge technology. But in the United States, we just didn't have the ability to replicate it over and over and over and over. So also one of the questions you're going to have to ask yourself, is there qualified labor to build the engineered designs? So you'll have an idea, but how do you get that idea to have someone else build it for you? Because you will never have the manpower yourself to build a large scale project. Some of these projects, like I have here, a major project may involve 10,000 people on the ground and 50 million plus man hours. So the last project I finished here in Houston, Texas, we ended up having 75 million man hours. We had about 10,000 people on site, and around the world, there was approximately 100,000 people that touched the project. So between the motors and the heat exchangers and different valves in almost any country except Antarctica where stuff was being fabricated. So how do you take that as an engineer, those ideas, put them on paper, and then send it to the Philippines or over in South Korea and have that person do exactly what you put down on your paper? All right, so some more of the barriers to development is, this was a project I was on up in Rajasthan, India. And so there's a 125 megawatt solar renewable project. And before we even broke ground, after we broke ground, but before we could actually build the project, we had to bring in 240,000 dump truck loads of dirt. So you're going to have a lot of things that you may have to do in preparation before you even start a project to be building an electrical grid. So this was a dry lake bed. And then this was actually a real life picture of a person who brought bricks to the project. And his donkey broke down. And I took that because I'd never, coming from the United States and then living in India, it was something that was so foreign to me. I could have gone back 1,000 years and not been more surprised. But here he is hauling his donkey while the donkey is eating to get it back to a place where he could repair his donkey and get more bricks to be bringing to the project site. And so sometimes when you think you have a technology that's very advanced and that you want to implement, it'll be a different story when you go to implement it in India or Thailand or somewhere in Asia, even in maybe some of the Middle Eastern countries. See, the tools that are available aren't necessarily going to be what you have available here. It was very common in India. There was a concept called jugaad. So you took what you had and tried to improve it. So if you didn't have a hammer, you'd take a long bolt and then weld a nut to it, and then you had a hammer. Well, it didn't work quite as good as a hammer, but it worked well enough. And so, but the problem is some of the tolerances, if you're creating a technology that works in microns or millimeters, they may not have the tools necessary or the resources available to build that. All right. And then also change in market conditions. When you go to build a large scale project, is it going to be viable 10 or 15 years later? One of the recent headlines in Bloomberg where they do talk about a lot of renewables. So in Europe, this is probably 3 weeks ago, is there wasn't enough gas, but coal is now making a comeback in Europe, believe it or not. And then Shell, if you ever seen the Shell gas stations, so Shell, the company, they spend about $15 billion on floating LNG, liquefied natural gas, but they've got it up and running, but they're not going to make any money on it. And it sounds like they're going to shut it down. So how do you have an idea that's a project that will actually last the design life? So will it last 30 years after you end up building it? Or is it something that people are just going to have to shelve it because they've lost so much money? One of the biggest challenges for building a project is, and you can't treat it as an evil word, even though some people do, but the company has to make a profit. It's not something where people should be throwing cash in the air and we're making millions and billions of dollars. But if a company's not making a profit, they'll end up going bankrupt. And then the people that are working on that project will no longer have paychecks. So a very quick way to shut down your project is to not make a profit. So always keep that in mind, whatever you do in your career, that you may have the best idea ever, but if it doesn't make a profit somehow, whether it be through subsidies or just selling the material or after you're up and running, your idea will get killed pretty quickly. And then also disasters can change public perception of where you put a project. Any idea what this picture is of right here? I gave a hint with Japan being March 11th, 2011. But any idea what project that was?
Andre, do you want to unmute?
That was the Fukushima Daiichi nuclear power plant that
Yeah.
had a reactor failure when the tsunami hit.
You're exactly right. And they've studied why it failed, and the diesel transformer should have been up higher, so they never would have had seawater get into it. It was a very old design. The reactors nowadays would never have that occur. But I share this with you because it impacted my career quite a bit. So in 2000, March 11th, 2011 is when that occurred. And so in February of 2011, so Eric Macbeth is getting hired by the world's largest nuclear company. So Kimberly confirmed and appreciates setting it up. So I go up for an interview to Bethesda, Maryland by Washington, D.C. And then Fukushima happens about a month later. And then a month later on April 6th, 2011, so not quite a month, says, Eric, we are excited you'll be joining the AES, which is the REVA nuclear team. And here's your offer. And so, think of 10 years ago when I was going through this process. I'm just hired as the youngest project director of this nuclear company. It's the world's largest. There were 75,000 employees. And the Fukushima accident had just happened. The United States was going through a nuclear renaissance at that time period. There was 10 reactors that we were up getting ready to build. You could not find enough people to build nuclear reactors. And this happened and public perception changed. And around the world, every reactor at that time pretty much just shut down as far as a project that people were going to build. So in Texas, they were going to build 2 nuclear reactors. In Florida, they had, I think, 3 nuclear reactors. And so those all got shelved after this accident. And people saw a nuclear disaster, but they didn't realize that that disaster would not have occurred with the newer designs that we have. So it's something that may set back a technology decades by having a public perception that may or may not be real. All right. And then, here's another challenge that you'll have with different technologies while you're developing an electric grid. Right now there's no way to recycle windmill blades. So people have ideas how to do it, put it in concrete, crunch them up, but they can't do it. And so, like, for an example, when you're building a power plant, or not necessarily a nuclear power plant, but normally if once they're going to retirement, they deconstruct them, sell off the steel, and you'll go back there a few years after they're finished decommissioning the plant, and you can't even tell that it was there. But like a lot of the things we have with windmills and solar right now is they're going to be going into retirement in the next 10 to 20 years. So what do you do with all that material that you've put up in the air? Because a windmill, for example, when you have the leading edge of the blade, especially when you're in sandstorms or areas that have a lot of material in the air when it's being blown, that acts like has anybody done any like sandblasting, or been in an area with a lot of sand, and what it does is it eats the paint off a car, or it's a cleaner. And so it does the same thing to like a windmill blade. And so it becomes very inefficient throughout its design life. And then, can anyone name this dam failure? And Brian's not allowed to talk, but I have a picture of a dam failure of a hydro project. Any thoughts on that one? This is before my time, just by a year. So probably most of you don't, but in the United States, go ahead.
Andre
Go
had a
ahead.
question, and then Patrick had a guess.
Okay.
So unmute yourselves in that order.
Sure. I think you answered it. I was just wondering, how long is the lifespan of a wind turbine? You said 10 to 20 years, depending on the environment.
Oh, so they'll have on your projects what they call a design life. And so if a windmill was put into service 10 years ago and it had a design life of 20 years, it would have generally 10 more years to go. Or if it had a design life of 25 years. So a lot of it depends on the materials and that they put into either the blade or the turbine itself. But on windmill projects, most of them have design lives of about 25 years. So they'll need to be decommissioned after that time period. Like a nuclear power plant might have a design life of 30 years, but they have the ability to extend that license. And so they might have 60 to 80 years out of that project. But you have to, especially when it comes to like nuclear or natural gas, you have to go in there and usually clean out the reactor head and put in new turbines. So there's constantly shutdowns that occur to extend that design life. So is there a guess on where this, I guess accident, but disaster occurred?
Is it Teton Dam?
Yeah, you're exactly right. You're exactly right. So Teton Dam, if anybody's ever been to Jackson Hole, Wyoming, on the Idaho side, there's a river called the Teton River. So it starts up in the base of the Tetons and then flows down through this valley in Idaho. And so the Teton Dam failure occurred in 1976, and that led to a total revolution in the public perception of hydro in the United States. So before that time, we were a dam building country on the Columbia River, the Hoover Dam, the Teton Dam, but that was one of the last large-scale dam hydroelectric power projects in the United States. And there's been a few more since then, but nothing on this scale. It was interesting when I came into the nuclear industry. The project engineers that were working on this dam were the same engineers. They're ready to retire, but they were working on nuclear projects at that time. And so we had always heard that there was just a leak in the dam and it flooded the valley. And fortunately, there was only, I think, 12 people that passed away. But the project engineers, when I heard the behind the story, was right here on the left-hand side of this dam. There, in this area, there's a lot of lava rock. So there's caves and there's fissures, and what it is it's the remnants of Yellowstone as it moved up the valley. So as Yellowstone Park moved up into Wyoming, Montana, it left behind all these calderas and caverns. Well, anyways, the Corps of Engineers, who is the United States kind of branch of building large infrastructure projects, these constructors it was the largest construction company at that time called Morrison Knudsen. They were sending in change order requests, so for filling grout alongside this wall over here, and they were pumping in hundreds of thousands of cubic yards of grout. And the Corps of Engineers said, guys, you can't be you're doing something wrong. I mean, you're wasting the grout, but you've got to stop it. And so they ended up just basically cutting off the flow of the grout into the side of the mountain. And what happened is that water, when they filled up the dam, leaked into those fissures that they had not fully filled up. And that's what ended up being a breach into that dam. But yeah, so your technology may be something that's very viable and maybe a very cheap form of energy, but if you have a disaster, like for example, today, probably one of the new technologies you hear on the news, even though it's old, is, how viable is hydrogen? Well, if you have a hydrogen explosion, which was like the Fukushima accident, but let's say you have a hydrogen container, your technology won't last too long. People will get very concerned and won't let it be in their neighborhood. All right, this is one of my favorite slides of the whole presentation. So the potential number of electrical failures per day. And this is where I give electrical engineers kind of a kudos on the back. So probably in the time I have just said the sentence, everybody's blinked once or twice. So that's something that we have all done. And during that time period to blink, we usually average about 100 milliseconds. Some people go to 150, maybe 200, but let's say 100 for mathematics. And so during that seconds, we have about 10 of those blinks. A milliseconds is for 1 second, there's 10 of them. If we went into the minute, the hour, the day, we have 864,000 of those milliseconds. Now, in the world of electrical engineering and projects and big fabrication facilities, so something that we would call a major event is the end user is something that lasts about 100 milliseconds. So this is what they call a voltage ride-through criteria. So if you're somebody that's consuming electricity and that you're relying on electricity to run your big electrical systems, or let's say you have a manufacturing line, you're building cars, or you're producing liquefied natural gas or big HVAC systems. So the sine wave, normal operations is 100% voltage. So everything's fine and dandy. But let's say there's some kind of kink in the system and you can lose up to 50% of that voltage. And here you have 12 cycles. And that 12 cycle period is 100 milliseconds. So your motor or whatever you're relying on as a company, it should last for about 100 milliseconds. Otherwise, it might trip it. And the reason why it gets tripped is to save the integrity of that machine. So here in Freeport, Texas by Houston, this happened about, it would have been 4 weeks ago. So you can see here your normal sine waves. And then all of a sudden it goes real wacky right here. Oops. And you lose your 50% and you got your 12 cycles. And then right here, you see where everything gets real tight. That means there was a basically it deadlines and it shuts down. So our plant went offline. And so what was the cause of this failure? And here you have the line coming off the feeder to the transformer. Can anybody identify what that was right there? It looks like a stick. This was this caused one of the largest shutdowns in Texas, and it's actually a snake. And so this guy was crawling around up here, and he touched 2 different points at the same time, and of course he fried himself, but he also shut down probably close to $150 million in production in one day. And we've had instances where bird poop, so from seagulls to birds, people that design these high voltage power lines rely on rainwater to wash them off. So if you have a high amount of birds that are flying around that land on them, and if it's going for a month without rainwater, that can also lead to a failure. So this little snake, he caused shutdown to this plant. This ship was not able to be filled up, and he had to take off. So there's $5 million a day production for this one little plant. You have a ship that it costs $300,000. You have one of the largest plastic fabrication facilities in the United States, Dow Chemical, that went offline. And for us on our plant, we were shut down for a full day because of one snake. So in our minds, we think that we have a very robust and reliable system, but in reality, it's very, very fragile. And so things I want you to think about for your future careers is how to make things more reliable so those instances can occur. On nuclear power plants, we have turrets. So we have guns that protect the facility, that to keep out people that we won't want in there because it's a national security interest. On this plant, we have it's regulated by the Coast Guard, and so we don't let people. It's a national security interest that they're not allowed to come in there. Anybody that's doesn't have a certain pass. But on like a nuclear power plant, if we have a turrets, there's places in California and other places that if one person was able to, and I remember hearing this from an old timer, and it always stuck with me, but if they had taken a bullet and put it through one of the transformers, then it would shut down like the Northern California electric grid, because and those transformers take 6 months to make. And so it's interesting how fragile the system is compared to what we just take for granted, that it comes into our house and turns on our lights.
Tomas had a few questions, if you're willing to take them now.
Yeah, go ahead.
I would like to ask what can be done to increase the security in nuclear plants, and why do these mistakes sometimes occur?
No, that's a good point. Let's go back here to this one. So for example, what can be done to increase the security of like a nuclear power plant? Not so much in the nuclear power plant itself, but when you go to design a plant and you're looking at transformers. So again, think of the word scalability. And if you have, on my last project, we had about 1,500 engineers. So of that 10,000 people, 1,500 were mechanical engineers, electrical engineers, piping stress engineers, structural engineers. And so you have a lot of people that have different opinions, or they bring their own, either their bad habits or good habits and their preferences. And so when they go to do a specification for a transformer, they may go with what they've always used. And so what may be a smarter idea is to spend a few extra $100,000 and have a standard that's, you could literally go off the shelf and buy this exact same transformer. So on a project I'm currently working on, we have about 700 transformers, and we have about 40 different styles or different models. And so we've talked internally, would it have been a lot smarter instead of having 40 different models to just had 2 or 3. So it would have cost us maybe $1 million more, but when a transformer costs you $600,000 in 6 months to get made, it probably would have been better investment to go with some type of standard that, you know, could have come here, and we could have had spares, that maybe 2 spares, because we can't afford to have 40 spares, but we could have afforded to have 2 or 3 extra spares. So that's one thing I would encourage you when you're going through your careers, and especially if you get into the design field, is whatever you're designing, don't make it so challenging to build that it's hard to replicate. One of the interesting nuances I've seen in my career is in Germany. So the Germans are probably the best for fabrication. So when it comes to valves and tolerances, gearing, for some reason, the Germans are the best. But where in the United States or Australia, if a tolerance is acceptable within 5 millimeters, so when something butts up against each other, for some reason, the Germans will always do 2 or 1 millimeter, just because they can. And so it works great in the optimum prime condition, but when it gets out into the elements and Mother Nature, one of your biggest challenges in your career will be dealing with Mother Nature, just like, you know, a dam breaking or a flood. I've had so many cyclones and hurricanes that I forget all the names, but if you're building a project and you're halfway through and then you have 3 feet of rain that comes through, and just imagine all the materials floating around. What used to be new is now covered in mud, but you still have to somehow clean it off and put it back up into place. So more on to the reliability, like in this, let me go back, this plant up here, this is what they call a liquefaction plant. So it takes natural gas and it puts it into cryogenic temperatures. And cryogenic means it's well below freezing, so about 250 degrees below 0. And they do that because the cryogenic takes natural gas and puts it into a liquid form. So a liquid form of a natural gas molecule is about 600 times compressed. So if anybody has a barbecue grill and they've taken one of those gas containers or seen their dad use it or mom, and liquefied natural gas container of that same size, you could expand it 600 times into an aerosol natural gas molecule. So these motors, just so you know, these are actually the largest motors ever made in the world. They were the first of their kind. Now there's 100 megawatt motors, but these were 75 megawatt motors that spun at the highest RPM. So there's actually bigger motors that they use for moving the space shuttle, for example, if you've seen it move to its ramp for launching. But those are very slow motors, but these ones spin at 3,700 RPM. So again, the 100 milliseconds will shut it down, these motors, and they do that to protect the integrity of the machine so it doesn't destroy it. But the problem is they go into what they call slow roll. And so what's a slow roll is you have your rotor over here that fits inside your stator. And as it's going from 37 to 36 to 34, that takes about 4 to 5 hours. Total stoppage is about 6 hours. And then it would take you 6 hours to get back up and running for production. So you can imagine how much, like on a liquefied natural gas plant, if you're producing probably 80 to 90 million dollars a day of revenue, you know, as a company, that could affect you. You can absorb that once or twice, but you couldn't do that once a month or twice a month. You'd end up, because you'd be paying your people to constantly fixing your plant. And then also, you know, this was a question we had just the other day from CenterPoint Energy, which is our grid utility. And so they'll talk about, quick question, can the plant confirm or deny if there's some sort of load imbalance within the liquefaction facility during the time frame that low voltages were seen? So they're asking, did we mess things up? And then you'll have to write letters to your contractor. So grid reliability is very important. This was something that always amused me, because when I was in India, this was in the village next to where we were building a project. I always thought, the project that we're building has very sophisticated technology, but this is one of the points that it ends up going to. So you can see all the oil transformers on top of the telephone pole. And if anybody's traveled overseas, you see this sometimes in South America, quite often in Asia. But if there was something that occurred in this disaster area, I mean, it would be really hard to decipher what really did occur. So just remember, your technology may be very sophisticated, but if it's feeding to something that is a public utility that doesn't have the same quality, what you have, may not end up working. So this was one solar project I was on over in India that turned out really well. This is on the left-hand side. It was in Rajasthan, India. So it's what they call a solar thermal. So it reflects the sun back up into a tube that's up here in the air, and then it creates superheated steam. It's above 330 degrees Fahrenheit. And so it runs just like a normal power plant. And then on the flip side, I was in charge of Australia. And then I was in charge of a project that we had for what they call a solar boost. And so this whole area right here is solar panels that never ended up getting used. You can see them stored over here. And this is a coal-fired power plant. And so the theory was build a solar boost. And so during the days when the plant wouldn't run as optimum because of the heat, you could use the solar, and that would offset the carbon emissions for the plant. And you're also getting electricity at the same time. But what happened is the project ran out of money. And then there were some cyclones that came along. The cyclones destroyed the tubes that ended up what they call absorber tubes. And so even though it was a great idea and it would have benefited that whole community in that area, it's something that, it was written about in the Sydney Morning Herald, fast moving clouds, how CS Energy's Kogan project, solar boost project failed. And then here I am, I had to go back and testify in Australia. So the day I graduated from MBA school at University of Chicago, instead of getting to spend my time with my classmates after graduations and the fancy dinner, I had to fly down to Australia and testify before their Supreme Court on this project and what occurred. So probably all of you will have some type of learning experience like that and go through depositions, hopefully not depositions, but why it failed. Was it a flop because of the technology? Was it a flop because of the environment? So we had to go through all those different scenarios of what occurred. So, all right, designing a grid. So here's just a question to think to yourself. Is bigger always better? And what advantages are there in a smaller grid? So there's reactors. This is a nuclear reactor station. And just for nuclear, when people see steam coming out of the cooling towers, a lot of people think those are emissions like SOx, NOx, but it's actually just water. So coal has emissions, but nuclear is clean. What you're seeing is water vapor. And then, some of the larger transmission yards, but definitely in your generation, and probably for mine at the end of, throughout the end of my career, you're probably going to see going from these large, 3,000, 4,000 megawatt projects to where you're going to have communities have anywhere from 200 to 600 megawatt type projects instead of having a centralized system. So I think I've got a picture here coming up, but instead of having a power plant and then you have a transmission and it going to the end user, you're going to have quite a few homes and people, a lot of battery technologies coming on, people that have solar on their houses. You're going to have that feeding back onto the grid. And so that's a distribution type technology. And so it'll be more smaller, nimble. It actually may be less connected than what we have now. So instead of having the eastern grid go down, you might have, select locations that collapse for a while, but it doesn't kill the whole system. This is another important concept: baseload versus intermittent supply. Any ideas what a baseload fuel is? And then what is an intermittent fuel? And this being a baseload fuel that would, for gas, solar. Is that hand raised?
Yeah, go ahead. There's Andre.
So your baseload fuel is basically your standard fuel that you use to keep up with the normal energy drain. But then there will often be spikes, especially I know a lot of power companies have trouble in the summer when people are running air conditioning units. And sometimes the baseload fuel isn't enough and they can't use more baseload fuel because they've already maxed out their plant's voltage or amps. I'm not very good with electrical terms. But then I know that some power plants, I know a power plant near where I went to school had a jet turbine next to it. And in the middle of August, they would fire up the jet turbine and run that as an intermittent supply to keep up with peak demands during the middle of the day. And that would use a high density liquid fuel as opposed to their standard gas fuel.
Yeah, that's exactly right. And the terms were perfect. So thank you. When you're designing a grid, let's pretend you're like a utility owner that's in charge of providing electricity for, your community or your state. So, you may have a nuclear, one solution may be, let's just go build nuclear reactors and provide 100% power at all times. So we'll take the peak demand and we'll design to that peak demand. Well, there's going to be quite a few times during the day when either A, you're sleeping, or the manufacturing facility has gone offline. And so that demand curve, it looks like an ocean wave. And so it's going up and down continuously throughout the day. And so you have people that are forecasting that. And it wouldn't make sense to spend that much money on reactors or coal or natural gas when that's one of the benefits of like a wind or solar technology is there's times when wind generally produces quite a bit. And it's actually very cheap energy. Its challenge is that it's not continuous. And so you can't treat it as a baseload fuel, but you can treat it as an intermittent fuel. And so the utilities, it's up to them to figure out, what's the right mix. I don't want to spend all this money on a reactor because I'm going to be wasting a whole lot of money at the times that there's no demand for that electricity. So it's just basically going to waste. But if I can get to where a base load is I'm comfortable with, maybe it's a 20-30% of my total demand is a base load fuel, and then I can supplement it with intermittent fuel, as far as being able to be very economical for your consumers, that might be the best option. Then I have just a question here. Do you think wood is considered a renewable fuel? It's more popular in Europe right now, but go ahead, Andrew.
For being really technical, I know people do consider wood as a renewable fuel because they consider it as part of the short-term carbon cycle rather than the long-term carbon cycle. And they say that when you burn wood, it is the emissions that are released are recaptured by the offspring trees in a reasonable amount of time. Therefore, it doesn't actually contribute to carbon emissions the same way you would as if you burned a long-term carbon cycle product such as natural gas, coal, or something along those lines. But I know there's different opinions.
That's right. Adam, did you have something?
Yeah, I was going to say that at least from what I learned, that would be considered renewable because it can be like readily replenished.
Yeah, it's always something that sometimes people that are in the fossil fuels kind of snicker or laugh at it just a little bit because on one hand, we want to plant more trees, but on the other hand, we want to burn more trees. But there's actually quite a few farms in South Carolina, Louisiana that are dedicated to building wood pellet facilities. And so the coal-fired power plants that are especially in Great Britain for some reason right now, but they grow the trees in South America, or not South America, South Carolina, harvest them, create wood pellets, ship them over the ocean, and then they burn them in those former coal-fired power plants as fuel. So that's something that the EU considers as a renewable fuel. So some of you probably know these terms and some may not, so we'll go over them. There's watt, and then KW is kilowatt, and then megawatt and GW. So watt is just, in electrical terms, it's the power used to move. That formula right there was 6.25 to the 10th to the power of 18 electrons. So that's a watt. Now that's generally what most of in your home, things will be measured in watts. So you might have a light bulb that's 40 watts. A lot of LED has come around recently, so you'll see the equivalent of 5 watts. Maybe, it equals used to equal a 75 watt light bulb, but it consumes 5 watts. A microwave probably is 1,000 watts. A fridge about the same. A toaster is maybe 400 watts. And then most of the time you'll see things on a more of an industrial scale measured in kilowatts. And then, do I have it? Yeah. So here's a pop quiz. How much electricity to the closest 10 kilowatt hour does it take to power your iPhone or Android for a year? 1 kilowatt, 10 kilowatt, or 100 kilowatts hour? Any ideas? And a kilowatt's generally what the utility prices to you, the consumer. So you might have anywhere from 9 cents to maybe, it's getting up there. It's probably closer to 35 cents per kilowatt that they charge you kilowatt hour. And so you get a utility bill that might be $300, $200, but that'll be based off kilowatt hour. But your iPhone generally uses about 1 kilowatt hour if you were to charge it for the year. So it's actually really cheap. I mean, we're talking in the cents, not dollars or hundreds of dollars. So if your parents give you a hard time for charging your phone too much, don't worry about it. A megawatt, if we go to like a power plant, it's 1,000 kilowatts, and then a gigawatt is 1,000 megawatts. I don't know if any of you are Back to the Future fans, but when he goes, to get that car running, it's a 1.2 gigawatts. And so the plant I'm on right now, we consume about 800 megawatts. And then we're building a train 4, so we'll consume about 1 gigawatt to run just that one project. So actually the largest electricity consumer in the United States. All right, so here's an important concept that you need to know when you're designing an electric grid. So if you put on your CEO hat and you're trying to supply power to electricity to the United States, there's pricing, demand, and supply. And so any ideas of the pricing for utilities like electricity, if it's elastic or inelastic? That's kind of more of a macro micro type question. So I'll answer for it. It's inelastic. So, as price goes up, you still demand the same amount. The problem with electricity, and this is one of the conundrums that we have to figure out as a society, is electricity. It's not like one is a Porsche and one is a Ford Fiesta or a bicycle, a very cheap bicycle, not expensive race bikes. But if you're a person that's renting and you have a fixed income, you've got $2,000 a month coming in, you're working as hard as you can, hourly, not even making $15 an hour. But if you have rent that's $1,000, your utilities are $300. Think about that person if their electricity increases by $200 a month, and their utility, now they're at $1,500. Something's got to give. So what happens is if pricing on electricity, if it goes up even 1 cent, 2 cents per kilowatt hour, all of a sudden that bottom part of your population goes from to where they can at least afford to rent to where they're now homeless. And so those are questions and concepts that you always have to keep in the back of your mind when you're building a grid, is can the people that we're building it for afford? They're either going to have to be subsidized somehow if they can't. So if we went with a very expensive technology, even though it might be the cleanest technology, especially when we're in, let's take like India and Thailand and Southeast Asia, we may have a whole slew of or not customers, but citizens that just can't even use it. And then, generally a developer will build a project and compete in a bid per megawatt to sell the utility. So, utility will say, we're going to auction off blocks of our megawatts at $35 a megawatt hour. And then the developer will say, oh, well, I can provide it for $32. And so he'll win the bid. But if he can't, at the end of the day, he's going to have financial damages and may not even end up being able to build the project. We'll move on to the next one.
We have a quick question from Vivian and then actually one from Brian, if you guys want to ask.
Go ahead.
What is the average amount of kilowatt hours a household uses per month, and how much does that add up in terms of money?
Well, the average is about 2 megawatt hours per house. And one thing that be very careful in, and this is not just in the megawatt hours per house, but always take it with kind of a grain of salt when people speak, in classes or online when you read news articles. And for some reason, especially when it comes to the terms in terms of electricity, people talk in the terms of averages, but it can change night and day based off of demand. So people will say, well, 1 megawatt will feel on a, well, let's see. Yeah, 1 megawatt will feel on the average X number of homes. The problem is if the demand changes, like let's say on one day it's 88 degrees, you might have, instead of 1,000 homes on average being able to use X number of megawatts, now you can only use 100 homes. And so when you're developing your demand profiles, something can change 80-90% just based off of temperature. And so just like when I was talking about the potential failures per day on the electrical grid, people will say, and when it comes to this summer is very important because like California and Arizona, even Texas, they're all talking about saving consumption on electricity. And then you'll see, well, our average of what we use is 69 gigawatts or 50 gigawatts, whatever it is. But if the temperature profile changes even a few degrees, it could change it by half. Instead of 50, they're using 25. And so like when I read popular science and they say that this project will produce and like a windmill farm will cover, let's say 10,000 homes on average or 1 million homes. I mean, those are at the very optimum conditions, at the very best of days we'll ever do that. And so it's really hard to say what's average because they're so different. But generally your house is going to be between $100 to $400 a month to heat, but every state is different. Does someone else have a question?
Yeah, as you were talking about, you use this project you're working on will use 1 megawatt of electricity. What will the output be? So what's you've got what you put in, but what comes out as a result?
Yeah, so we use electricity it's like a giant HVAC, heating, air conditioning system, and also in compression. And so there's not necessarily a translation of, because we take the dollars of what it costs per megawatt, and then the output is $1 of liquefied natural gas. and they may not use it for a megawatt hour. They might use it for something else of just heating, which doesn't produce electricity, but it's a different energy output. But we generally, our tolling revenue is $5 million a day, and we have about 80 to $100 million a day of gas revenue that gets shipped over on boats. And the electricity consumption costs us right around $150,000 to $200,000 a day.
Thanks. Oh, Lauren had a great question.
Go ahead, Lauren.
There have been movements that want to convert to 100% renewable energy. Do you think this is feasible, especially in low-income areas?
No, those are good questions. I mean, I've spent part of my career on renewables, and it's a great concept. The concept, though, can it be a baseload power supply? So it's something that you'll see in the news quite often, that people talk about the supply side. So they say, well, shut down all natural gas, shut down all coal, maybe nuclear, but they never talk about the demand profile. And so when you start looking at the demand profile, like for us, we ship liquefied natural gas overseas to Asia quite often, and Europe. So it's not like they don't have another fuel source. And like Japan never will be able to have a fully 100% renewable fuel source, at least with the technology that we have today. You could transfer to wind, but there's no way to store enough electricity to then fuel their society, for the times when they need it. And so there's this disconnect of demand and supply. And so a lot of times people talk about the transition, you'll hear, and that transition is, no one's quite sure yet. Is gas the transitional fuel supply to get to a renewable technology? No one knows yet. Was there another question? But yeah, then there's go ahead, Daniela.
Hi, so I basically watched the TikTok by I'm not TikTok, sorry, TED Talk by Michael Schellender about how basically non-renewable energy and renewable energy are both like equally as bad. And since you spent your most of your career studying like renewable energy, do you agree with this statement?
Well, I've kind of spent on all of the sides, I guess, now with nuclear, gas, and solar. But was his comment that they were both bad, or?
He was commenting that at the expense of saving like renewable energy, we're also like causing a lot of environmental damage, such as like with solar panels and like wind turbines. And you kind of went into like the damage that wind turbines can cause.
Yeah, I mean, there's examples of it, and I don't necessarily say that to put, I guess, knock on them or put them in a bad light, because all technologies have challenges. I mean, there's positives and negatives to each of the technologies, and that's something that people internally have to evaluate. So you can't necessarily take one technology and say that'll never work, or that's the only way to go, because there's multiple sources and ways to fuel society. And something that I learned through my career, and it was surprising to me, is like maybe sometimes on the procurement cycle. So when you go to buy 75,000 tons of steel or solar panels, it's got to come from somewhere. And so sometimes the cheapest option is not the best option, because if a person is offering something cheaper, like a solar panel versus another supplier, maybe they don't pay their labor as much. Apple ran into that problem a few years ago with China. Is iPhones were being produced very cheap, but maybe the fabrication facility they're building in wasn't paying their employees, a normal wage of what would be normal for that area. So on, oh, go ahead, Tomas.
I wanted to ask you about I think many people say that nuclear plants, I mean nuclear energy, is dangerous for our environment. But is this true?
Dangerous? Yeah,
Yes.
there's definitely precautions that need to be taken with nuclear. As far as saying, after being in the industry and seeing all the safety precautions that they take, for me, it's probably the most reliable, safest fuel source out there. It's something that I came away from it with a new respect of how much time is put into it and the different layers of safety they have. But on the flip side, there's the whole, like when I went to India, I had to have a different kind of computer because of there's certain countries that don't have nuclear proliferation treaties with the world. And so you have to take that into consideration, that you don't want that technology getting into the wrong hands. And so how do you protect that technology? It's always a big question and a challenge.
Okay. Thank you.
We've got about 7 minutes. If you wanted to finish up what you had, Eric, and then get to any questions after that.
Okay, well, I'll hurry through this, guys and ladies. And so this was just a slide on the different utility pricing. So if you look at the bottom, Connecticut's 20 cents per kilowatt hour, Alabama's 12 cents. So yeah, if you're using multiple kilowatts, that's quite a big difference. Especially if you're a CEO wondering where to put your next facility in the United States, and you're wondering about electricity prices. So this is just another slide on centralized versus distributed generation. And now, Brian, will this be on? You'll save this presentation, but it'll be accessible if they want, right?
Yeah, we will put it on YouTube for them.
Okay. All right. So this is the different kinds of distributions that we were talking about before. This is another concept that's important to comprehend: nameplate capacity versus efficiency. And let me go to this next, let's see. So right here. So when people talk about they have a 100 megawatt project, that's not really what that project produces. And so I'll always keep that in mind when you read a newspaper article and they say 100 megawatts. Well, that's the nameplate capacity factor, but the actual production factor could vary. You know, solar is down to 24%, wind is 34%, nuclear is 93%. And so that's the amount of time that it'll be up running. So, you know, of course, wind is one of those intermittent fuels that we were talking about. And so this is an intermittent fuel demand profile for a typical utility like in Texas. And as you see, in the different times of day, it changes by anywhere from 40,000 gigawatts to or megawatts to 60,000. So there's a 20,000 megawatt difference throughout the day. So a 20,000 megawatt difference to make up and also take off the grid. It's, you know, that's 20 Hoover dams, to put that into context, that you have to put online and take off during the day. Now there's Hoover Dam. So this is right now with the drought conditions they have out west. Like, how do you deal with like a hydro facility that doesn't have enough water behind it? So this was a news article from just this week. They're at 66% efficiency these days. So you have 2,000 megawatts that are potentially available. That's the nameplate capacity, but only half of it really is available. So if you're a utility grid, where are you going to get the rest of those electrons from? And then this was the challenge I had for the next steps of building, you know, an electric grid. So is it next Monday, Tuesday, or Monday and Wednesday?
Monday and Wednesday, yeah.
Okay. So my thought was, I wasn't sure how many people would be online, but we take 10 or so different technologies that would be available. And we have a country that wants to develop an electric utility grid. And so how would you mesh the different technologies from your nuclear, geothermal, biomass, solar to develop an optimum grid for the citizens? And it's something that has to be reliable. It's something that you'd have to figure in the peaks and valleys, and you don't want to be producing, 1,000 megawatts, but the demand is only 500 megawatts, and you're missing out on all, that's just something that's going to waste. Let's see, and then, so that's the challenge, and that'll be up online, and then just some of the resources.